The next conic section that we're going to focus in on is called the ellipse. Now the ellipse kind of looks like an elongated circle or an oval, some people might call it that. Here's a diagram, that's my hand drawing. It's kind of a circle that's stretched out in one direction or compressed in a direction, you could think of it that way. Now the definition of an ellipse is a set of all points, the points on the outside here, the sum of whose distances from two fixed points is constant. Now the two fixed points are called the foci, okay? Focus 1, focus 2. Now the points on the ellipse, I'll call them P for now. It says that it's the set of all points, the sum of whose distances, so you add up the distances from two fixed points, and it's constant. All right, so what that means is if I start at this point, P, and I take the distances to the two foci and add those together, okay, so I get two different distances there, right? One to each focus. So that would be, on the first one here, that's the distance from P to F1, and the distance from P to F2. The sum of those two distances, the sum of this one and the sum of that one, I'm sorry, the sum of them, this one plus the other one, the sum of the two, is constant, which means if I move this point somewhere else along the ellipse, these two distances add up to the same amount. The individual distances may change, but their sum remains the same. All right, and so if I were to move that point P, let's say I moved it over to here, okay, then again you have two distances, one distance to F1, the other distance all the way over there to F2. Again, the individual distances change, however their sum remains the same. Right, so dPF1 plus dPF2. Now I've got the P's aren't the same. There's a red P and a green P, okay? And so those distances, the sums are the same. Even though the individual distances may be different, their sum is the same. Now there are ways to plot these or draw them by hand. One neat example, if you take a sheet of paper, put a couple tacks on each at the foci, and then take a string. The length of the string is equal to that sum, right? The length being the sum. Of course, the length of that string needs to be greater than the distance between the foci. And you take your pen and stretch it out between them, then the string kind of makes this triangular angle with your pen being in the interior somewhere, and then you just kind of run that around, fixing the ends of the string at the foci, kind of pinning them down on the paper. You can run that pencil or pen around, keeping it taut or keeping it tight to the string, and it will graph out an ellipse. Kind of a neat way to do that. What I want to focus in on is coming up with the equation of one of these things. To do that, we're going to use the distance formula. We've seen the distance formula used before for circles, also for parabolas. And so now we're going to be using them for using it to derive the equation of an ellipse. What we're going to do is we're going to position the ellipse in a very useful way, and then we're going to show how we can shift it around and change it a little bit. So now I'm going to erase some of the markings inside my ellipse. I definitely don't want to erase the ellipse because it took me a while to get that drawn so it actually looked decent. All right, and now I don't want these 2 points on the outside either. So I'm going to get rid of those. Okay, close enough. Now, what I want to do is I'm going to plot my two axes, my x and y axes. And I'm also going to give you one more definition. There's a point halfway between the two foci. It turns out there's going to be some symmetry to this, but I'll save that for the end. A point halfway between the foci is the center. Okay, kind of like the center of a circle, but defined differently. Ooh, that marker's not very good. So, right there, we're going to call that C, point C, and so the center is halfway between F1 and F2, between the two foci, all right? Now, what I'm going to do is center this at the origin, make the center the origin. And so my y-axis is going to extend vertically, and my x-axis is going to extend horizontally through the center. All right? That gives us an x and y axes. Again, center is at the origin. Now, we can put some coordinates on these points, and I also have another definition for you as well. So there are 4 really important points and 2 important line segments. We have what we call the vertices. They are the intersection of the line that goes through the foci with the actual ellipse. We'll call these vertex 1 and vertex 2. The line segment that goes between the foci from one to the other is called the major axis. Okay, so the major axis is the line segment across the ellipse through F1 and F2. All right, that's the major axis. V1 and V2, the vertices intersect, or they're the endpoints of the major axis. So we'll say V1 and V2 are the end points of the major axis. Okay. Now, similarly, the minor axis, I suppose you can assume that the minor axis is the one perpendicular. It's the shorter, well, in our case, the shorter one. It's not always, well, it will be the shorter one. So, the minor axis is the line segment across the ellipse, and it's perpendicular to the major axis. Running out of room, but I think I squeaked it in there. Perpendicular to the major axis, okay? Also going through the center. Okay, so there are, so I've got the 2 vertices, and I also have 2 other points. They don't really have a name, but I'm going to put them up there. It's the endpoints of the minor axes. We don't really have, at least this textbook doesn't have nice names for those. What I do want to do is put some coordinates to these points. The ones in particular, obviously the center there is 0, 0. So I'm going to label these out here. Center is at 0, 0. These other 2 points, the one up on top here, I'm going to call that 0, comma B. So it's B units high. And the other one is going to be equal distance negative B. So 0 comma negative b. The vertices, I'm going to save the coordinates of the vertices until later on. We'll come back to that. The foci, the foci are actually going to be at, we're going to say they're c units from the center. It's kind of inconvenience to call that c, but that's okay. So this is going to be at negative c comma 0, and this is going to be at c comma 0. I'm going to actually erase that label for the center because that may be confusing with what the c is. Those are lowercase c's as opposed to the capital C for center. Okay, so that gives us some coordinates. Now, there is one other really important feature to this graph, and that is the hypotenuse. If you were to look at a right triangle here, on the minor axis and the major axis, if you were to connect point 0b to point c comma 0, if you were to connect those, you get a right triangle. And the hypotenuse to that right triangle, I'm going to call A. Now, what's nice is that there's symmetry over on the other side. The same distance is also A. Now we know that any point P on this ellipse, the sum of the distances is fixed. Well, for the point 0b, the sum of those distances is 2a, right? It's a plus a. Well, that must mean that every other point on this ellipse has the same fixed sum. All right? So in our example here, that fixed sum must be 2a, all right, by definition. And so, I can do these, how do I want to write this? I can do the two distances, and I'm going to go ahead and go from this point up here at the top. It's kind of a convenient one to use, but I know that it's the same distance all the way around. The sum is the same. All right, and so we're going to use a p-value. Let's put p anywhere on the graph. It doesn't matter. It's going to be x comma y. And so I'm going to use that point for my distance formulas. But I do know what the distance is. It's 2a. All right. So that means the distance from P to F1 plus the distance from D from P to F2 must equal 2a. It's a plus a, right? Because every point has the same sum. The distance is constant, the sum of the distances. All right, so now I just figure out what those two distances are based upon the distance formula and the coordinates that I have. So for the distance from P to F1, that's going to be the square root of the difference in the x coordinates, so x minus negative c squared, plus the difference in the y coordinates, it's y minus 0 squared. All right, so there's the first one. The second one is going to be the square root of, again, the change in the x coordinates, that's x minus c this time, squared, plus the change in the y coordinates, that's y minus 0 again, squared. And of course, that sum is equal to 2a. Tweak that a little bit, get it to fit. Then I'm going to simplify each of these roots. So on the left side, I get the square root of quantity x minus c squared plus y squared. Plus over here, I get the square root of, this should be plus d, right? Double negative, I missed that. This would be x minus c squared plus y squared again equals 2a, all right? Now our goal in simplifying this is going to be to isolate one radical and then square both sides to get rid of that radical. And then you're going to create another radical on the other side. You have to isolate that, square both sides again. So there's a little bit of algebra involved here. I'm going to try to go through it kind of quickly because I don't want to lose you in it, but I also want you to see where all these formulas come from. So what I'm going to do is I'm going to isolate one radical by moving the other one to the other side. So I'm going to have the square root of x plus c squared plus y squared equals 2a minus, because I got to subtract this root, the square root of x minus c squared plus y squared. Okay? So I just subtracted that root to both sides. Then I'm going to square both sides of this equation to get rid of the root on the left. When I do that, it conveniently eliminates the root. But on the right, it does not, because when I'm squaring the right-hand side, I have two terms. I have first term minus a second term. And when you square two terms, you have to use the perfect square trinomial formula or basically expand it all out and distribute, which is a little bit of work here. So on the left side, it's very nice. The square and square root disappear. You get x plus c squared plus y squared. That's all I have left on the left side. The right side, when I square two terms, we use the formula a plus b squared, or in our case, it's a minus because we're subtracting. A minus b squared is a squared minus 2ab plus b squared, a perfect square trinomial formula. And so I want to take the first term and square it. Well, 2a squared is actually 4a squared, 2a all squared. Then I have minus 2ab. Well, minus 2 times the first term times the second term. My a's and b's make it a little bit confusing here, but basically you take the first term squared, take 2 times the first times the second. Well, 2 times the first is already 4a, times the second term is my root, x minus c squared plus y squared. And then I get b squared, which is just the second term squared, right? So that's my root squared, which eliminates the root and just gives me the stuff under the root, okay? So when I get the b squared here, that's just the second term squared. Take that whole second term squared, it just drops the root off, okay? Well, now I can do some combining. What's nice about this is that my y squares will subtract out, right? So I'm going to subtract a y squared. That's nice. Those drop out. In addition to that, if I expand the quantities here, I'll get some more things to drop out. So I get, let's see, x squared plus 2xc plus c squared. That's my left side. That equals 4a squared minus 4a times the square root. And then here, if I expand, I get x squared minus 2xc plus c squared, and those dropped out. And so here, I can actually subtract an x squared from both sides. That will drop off the x squares. I can subtract the c squared. That will drop off the c squares. So some of this stuff simplifies very nicely. And then I'm going to rewrite this in a moment, but I can get lower here. So I can also add 2xc to the left and the right. Now those won't drop off, but they will combine over here into 4xc. I could also subtract off the 4a squared on both sides. Now, that doesn't combine with anything, so I'm just going to throw it in over here. So now I'm going to get, what, 2xc minus 4a squared, drop off there, equals negative 4a square root of x minus c squared plus y squared. Ultimately, my goal here is to isolate this root and then square both sides again. All right, so it does get to be a tad messy. Oh, one thing I noticed here is that I added that wrong. 2 and 2 makes 4, right? So that should have been 4xc minus 4a squared. Okay, one thing I can do real quick, and that's really important because I can now divide out the 4 from every term. Divide by 4, divide by 4, divide by 4. All the 4s basically drop off when I do that. Oh, I'm going to have to do a little erasing. I hate to erase this stuff, but it's going to have to be done. There's not enough space otherwise. Let's save what I can. And what I'm going to have is xc minus a squared equals negative a times the square root of x minus c squared plus y squared. Okay, and so now I should be able to square both sides of this to get my solutions. So I'm going to square both sides. It doesn't make a lot of sense to divide out this negative a at this point because if I do that, I end up with a fraction over here. And then when I start squaring it, I don't know, it gets a little bit messier. So I can square things at this point. That shouldn't be a problem. So if I square the left side, square the right side, when I square this, I'm going to expand it out. Now again, expanding requires me to follow this formula. The a's and b's get a little bit weird, of course, but remember it's the first term squared, double the product of the terms, and then the second term squared. So first term squared is x squared c squared, double the product in the middle, so it's minus 2xc a squared. I'm sure probably should put those in a different order, but that's okay. And then I got to square the last term, so that's an a to the fourth. Yep. And then over here, negative a, when I square that, I just get a squared. Then I square this root. Now notice here I don't have to use the formula because I'm not doing an operation in here. Sorry, I'm adding or subtracting, I'm doing multiplication, which I can distribute the square to. So when I square the root, I just get x minus c squared plus y squared. It's probably best at this point to expand everything out and then try to eliminate some terms. So I get x squared c squared minus 2xc a squared plus a to the fourth equals, now over here if I expand that, a squared times, that's x squared minus 2xc, that's a c squared and a y squared on the end. Right, so these three terms come from the bottom of the squared. Then I distribute the a squared, and I'm going to get some stuff to drop out, which is convenient. At least I'm supposed to, and if I don't, I probably made a mistake. I don't think I have. So that's x squared c squared minus 2xc a squared plus a to the fourth equals a squared x squared minus 2xc a squared plus c squared a squared plus y squared a squared, distributed a squared all the way through.
And now I've got a minus 2xca squared minus 2xca squared. I want to get rid of that, so I'm going to add that to both sides. 2xca squared plus 2xca squared. What else can I get rid of? Anything? There's an x and a c both squared. No, it looks like everything else is pretty much set, isn't it? So I'll get rid of those terms, and I get x squared c squared plus a to the fourth equals a squared x squared plus c squared a squared plus y squared a squared. All right, well, not great, but it's something. What I can do at this point is regroup some things and try to factor a little bit. Maybe I can get out, oh, let's see. I'm kind of looking ahead here. Oh, yeah, the x squared. Let's try to get out the x squared. So let's group these two terms together. I'm going to subtract the a squared x squared from both sides. And I think I'm going to leave this term over there as well and move everything else to the other side. So I'm going to pull, let's see. Let's subtract that one. So I'm going to get x squared c squared minus a squared x squared, right? So let's subtract that one over. I'm going to also subtract this one over, so minus y squared, the a squared. Then I'm going to move this one to the other side, so it equals this term, c squared a squared minus a to the fourth. That looks good, okay? Then I'm going to do some factoring. Out of these two terms, I'm going to pull out an x squared. So I get x squared times c squared minus a squared minus y squared a squared. And over here, I'm going to pull out an a squared, and I get c squared minus a squared when I do that. Okay, so just do a little factoring right there. And what's cool about this is I've got a c squared minus a squared and a c squared minus a squared. Well, let's think about that for just a minute. What do those represent? Going way back to our triangle over here, we have a Pythagorean theorem, if you'll recall. I've got a on the hypotenuse. I've got essentially c as the horizontal side and b as the vertical side based upon where those coordinates are. And so I know from Pythagorean theorem that according to this, now the c squared plus the b squared equals the a squared. That's the sum of the squares of the legs equals the square of the hypotenuse. And so if I rearrange that a little bit, I could, see that's c squared minus a squared. Yeah, I can just subtract, right? So I can take c squared minus a squared must be negative b squared if I subtract the a squared and subtract the b squared over to the other side. Now this, of course, assumes that a squared is going to be bigger than c squared because I get a negative here. The negative must be bigger, but that makes sense because a is the hypotenuse, so it's got to be bigger. So that makes sense. So this should be negative b squared. This should be negative b squared. And so I can, let's get rid of some of this. Right? And so I get x squared. I'm going to replace c squared minus a squared with negative b squared. Right, here's a minus y squared a squared equals, this is a squared times, again, negative b squared right there. Well, I've got a negative on all three terms, so let's just divide out the negative 1. It's coming together very nicely now. When I divide out the negative 1, I get x squared b squared plus y squared a squared equals a squared b squared. Notice that the a squared b squared shows up quite often. It's very convenient at this point to divide both sides of the equation by the a squared b squared. It eliminates a bunch of these factors. And so if I divide by a squared b squared, divide here by a squared b squared, and divide here by a squared b squared, then I get a bunch of things to cancel off. My b squares, my a squares, and here everything. And I just get 1. And so my formula then is going to be x squared over a squared plus y squared over b squared is equal to 1.
This formula is the general formula for the ellipse, centered at the origin. And again, I have these labels on the A, B, and C accordingly. All right, and so what happens there is that the B obviously corresponds to the two endpoints in the y direction, which is very nice. But watch what happens now with the A and the X. Remember I reserved labeling the vertices until the end. But now to find those values, those coordinates, obviously the y value is 0 because those are x-intercepts, okay? So to find, let's do this, to find v1 and v2, we let y equal 0 because that's going to be an x-intercept again, or two x-intercepts. Plug that in, I'm going to get just x squared over a squared equals 1, right? This whole term will 0 out. And then if I multiply both sides by a squared, I get x squared equals a squared. I take the square root, or use the square root property, and x is going to equal plus or minus a. Well, that's very handy, because what that means is that my vertices end up with an x value of plus or minus a. So this vertex 2 is just going to be a comma 0. Vertex 1 is negative a comma 0, right? that's pretty neat how that works out. And what happens then is that in our formula, really like this formula, the b value, the square root of the denominator, gives you the half the length of the minor axis. The a value, which is the square root of the denominator on x, gives you half of the distance of the major axis, okay? And then you have to have a 1 on the other side to make that work out. If you don't have a 1, you simply divide the entire equation, both sides, by whatever value is there. If it's a 3, you divide by 3. And then you determine what the a and the b value are. But you must have the 1 on the other side to do that, okay? So this, again, is the general form of an ellipse. And so the major axis has length 2a, and the minor axis has length 2b, all right? Now that's true whenever the a value is bigger than the b value. You get this longer x direction than the y direction. But if you flip those, if the b value happens to be bigger, then it's the major axis that's in the y direction and the minor axis in the x direction. All right, so whichever one of these is bigger gives you the orientation of the ellipse itself, okay? If the b value is bigger, the denominator under the y squared, then that tells you it's oriented vertically, and the foci are going to be on the y-axis. If the a value is bigger, then that tells you the x direction is wider and the foci are on the x-axis, okay? In addition to that, if we wanted to shift this graph off of the center, off of the origin, so that the center is not on the origin, then whatever the center's coordinates are will then be h and k, and just like we normally do, we get the horizontal and vertical shifts of the graph. And so in general, you would have x minus h squared over a squared plus y minus k squared over b squared equals 1. The center, again, is going to be at h comma k in this example. That gives us our two shifts. If a is greater than b, then you have this relationship here, where the major axis is 2a and the minor axis is 2b. So major is 2a, minor is 2b. If it's the other way around, and so if a is less than b, then you have the minor axis as 2a and the major as 2b. That should give you most of the information then regarding the derivation of the formula. Next we'll do some examples.